Different ways to reduce greenhouse gas emissions in pipelines. Dr. Jun Zhang, John Anderton, Atmos International Limited, Manchester, United Kingdom. Adrian Kane, Atmos International Inc., California, U.S. Pipelines are essential for keeping the lights on, homes warm, plants running, planes flying, and water flowing. They also provide one of the safest means of transport. By taking some effective actions, they can contribute to the reduction of greenhouse gas emissions significantly. We would like to explore a few ways for pipeline companies to help combat climate change. There are, of course, hardware solutions, carbon capture at station equipment such as compressors or heat exchangers. Although undoubtedly these solutions work, they are slow and expensive to implement. What we're going to look at are solutions that can be implemented using existing software tools or making a relatively small investment in a new software. The first and most obvious way is the implementation of an effective leak detection program as defined in API 1175. The second way to reduce emission is through the optimization of fuel gas consumption by compressors. The third way is through the improvement of network operations. With the move to hydrogen and renewable natural gas, pipeline simulation software can also help the pipeline industry to transit to greener energy, thus less emission. If leaks can be quickly detected, the pipelines can be isolated and repaired with a minimal amount of fluid leaked, thus reducing the greenhouse gas emissions. Many leaks are detected by the public through identifying liquid on the ground or picking up the smell of gases containing odorants. However, greenhouse gases such as CO2 and methane cannot be seen with the naked eyes and are odorless. The best way to detect these types of leaks from pipelines quickly is through a real-time leak detection system. The following examples will demonstrate the impact of the leak detection culture in reducing the consequences of leaks, thus emissions. Example 1. A long gas transmission pipeline. This example covers a 568-kilometer or 353-mile section of a long gas transmission pipeline across 3 countries in Europe. The customer is fully committed to emission reduction targets. The inclusion of a real-time pipeline leak detection system forms part of the emission reduction strategy. The leak detection system is based on a real-time transient model, RTTM, that simulates the whole pipeline based on measured flow, pressure, and temperature, and monitors the total pipeline volume balancing using SPRT, Sequential Probability Ratio Test. The system was commissioned following the startup of the pipeline. As part of the performance assessment, leak tests have been carried out on the pipeline. The leak detection section where the leak was conducted is 568 kilometers or 353 miles long, with block valve stations placed approximately every 30 kilometers or 19 miles. This figure shows the performance of the leak detection system, including the inlet and outlet flow, line inventory, leak alarm, leak size, and location estimate. If the customer didn't have such an effective leak detection system, it would not be surprising that the leak may remain undetected for many hours or even days. The early detection and isolation of the leak due to the leak detection system would reduce the gas release by 20 times. This will contribute directly to the reduction of greenhouse gas emissions. Example 2, a gas transmission network. This example covers a gas network of 1,200 kilometers or 746 miles, with diameter range from 2 inches to 24 inches in Australia. The network includes 6 supplies and 46 demands with the operating pressure between 50 and 90 barg, 725 and 1,305 psig. A real-time transient model, RTTM, was implemented to help the operators manage the pipeline capacity, operational planning, and perform leak detection. This figure shows the layout of one looped section of the gas pipeline network. The trends in this figure show the overriding of the offtake flow meter, the measured and calculated pressure for the 2 meters nearest to the leak point, and the statistical leak detection parameter. The above 2 examples demonstrate that effective leak detection systems using real-time transient models can help reduce gas emissions by a factor of 17.8 to 20 times. Since one of the main greenhouse gas emissions is caused by compressor stations in a gas network, the optimization of fuel gas consumption can make a big difference to the emissions. The overall aim of a gas optimizer is to allow operators to operate their networks more efficiently. Only with recent computing advances can this be achieved by using the massive computational power of the cloud. to explore a much larger number of possible operating scenarios for a given gas day plan that could be considered by a human operator or a single computer. The optimizer will then identify and recommend an operating plan that requires the least energy, emissions, or cost. The optimizer can also perform a comparison between the proposed plan and the current plan, assuming one is available. Integrating the optimizer with an online simulation model ensures the starting point for the process is accurate, and that the operational plan produced by the optimizer is viable considering constraints such as maximum or minimum flows and pressures, and intraday or end-of-gas day line pack requirements. This figure shows an example of the potential energy savings in a gas transmission network of 2,600 kilometers, or 1,616 miles, with diameters of 32 inches to 16 inches. A total of 112,200 megawatts per hour can be saved per year. The reduction in gas consumption by 10,635,000 normal cubic meters, or 375,571,000 cubic feet, contributes directly to greenhouse gas emission reduction. As shown by the assessment of Marco Gas and some gas pipeline operators, gas venting is one of the main sources of methane emissions. This could be caused by purging for works, regular emissions of devices, starts and stops of compressors, and unexpected incidents. It is therefore important to improve network operations in order to reduce the venting of gas. Pipeline simulation software can be used to provide operational support, such as capacity evaluation, which can address the complex and time, cost, resource consuming effort needed to establish the accurate capacity of complex gas networks for short and long-term gas network planning and transport commitments. This figure gives an example how Gasco use look-ahead modeling to evaluate nominations before they schedule their operations. By continuous monitoring of the pipeline inventory and pressure, they operate their subsea pipeline network safely and efficiently without breaking any contractive agreements. The above combination of real-time simulation and look-ahead modeling can prevent gas venting when the pipeline pressure increases, thus reducing greenhouse gas emissions. Maintenance planning is another area where the simulation software can help so that minimum venting is required before a job is carried out. There is little doubt that hydrogen will play a major role in the transition to carbon-neutral energy. The transportation of hydrogen blends is going to have a significant impact on the pipeline industry. To help with the transition to hydrogen, pipeline simulation software will be an essential tool. This figure shows a theoretical transmission network, currently transporting natural gas that will potentially be repurposed to transport hydrogen or natural gas blends. What we need to know is, can the network cope with the predicted future demand, and how will the concentration of hydrogen affect network capacity? A base case is constructed using the current MDQ, maximum daily quantity, at all demands as per this figure, a total demand of 345 terajoules per day. This case gives us the starting point for the analysis. The analysis repeats a 24-hour cycle, enough for the network to reach steady state at new conditions, with the total demand increased every 24 hours apportioned as per the starting state. A hydraulic simulation software makes this an easy task with the demand group feature. Demands can be added to a group, in this case all demands are added to a single group, and the input to the scenario is one single overall demand figure. Once the minimum pressure constraint is violated at any of the demands, we can see that the overall demand is reduced to maintain pressure. The point at which this happens shows the maximum capacity being reached. The results of the case are shown in this figure. It can clearly be seen that the maximum capacity reduces as hydrogen concentration increases. The maximum capacities calculated are as follows. 100% natural gas, 900 terajoules per day. 10% hydrogen, 850 terajoules per day. 25% hydrogen, 750 terajoules per day. 50% hydrogen, 700 terajoules per day. A simple study like this can determine if future demand can be met or if the network reinforcement is required. A good leak detection program can help pipeline companies reduce greenhouse gas emissions in the case of a leak. When utilized properly, simulation software and optimization applications can enable operators to make decisions that not only maintain security of supply, but also reduce operating costs and greenhouse gas emissions. They are only part of a bigger solution, but until we achieve the goal of 100% green energy, Everything we can do to make conventional energy cleaner is more important than ever.